The last part I'm going to talk about before we move on is power quality and harmonics. Here I've shown another simple circuit in the middle where we've got a voltage source on the left, a diode, and then a resistor shown in red, which represents a load. This circuit is known as a half-wave rectifier, and what it does is it takes AC power, which is shown on the left in blue, and converts it into an approximately DC power on the right, shown in red. But what does this do from a harmonic perspective to our grid? The Fourier series states that we can express any reasonably continuous periodic function as a sum of a series of sine and cosine terms. Looking at the example from before, we can express our half-wave rectified waveform, shown in red here, as a sum of sine and cosine terms. The first term in this Fourier series is always going to be the DC component, which is the average voltage that this waveform would look like if we had a DC load. Here it is shown in blue. It has a magnitude of about 73 volts, and of course the frequency is 0 Hz. But to make it look a little bit more like the red waveform, we're going to sum in a fundamental component with a frequency of 50 Hz. Here it is shown in the dotted green line, and if we sum this component with the previous DC level, we see a net waveform shown in blue that looks a lot closer to the half-wave rectified waveform we expect to see. This new component, of course, has a frequency of 50 Hz and an amplitude of around 130 volts. But we're still not quite there. Let's add in the next harmonic. Here it is shown again in the dashed dotted line, and the sum, now shown in blue, is approaching much more closely the waveform we expect to see in red. This component has a much lower voltage and has a frequency of 100 Hz. We can keep adding these terms up to an infinite number, and eventually we're guaranteed to perfectly replicate the original waveform. But you can see with each new term that we've added, we're getting closer and closer, and the degree to which that term contributes is smaller and smaller. So these higher frequency harmonics are less important than the low frequency terms. Just for completeness, here's the fourth harmonic, in this case at 200 Hz. So what do these harmonics do to our grid, and why are they a problem? Well, in the real world, we don't have any such thing as a perfect diode. And so those harmonics that are generated by rectifying that waveform leak across that diode and end up back in our grid. And they distort the shape of the original waveform, which I've shown on the left there. We can see that the sinusoid is no longer a perfect sinusoid. And remember, this is the same waveform that feeds all of the circuits that are connected to this particular source, which may be everything within your house, but it could also be everything that's connected to your street or to your suburb. And so harmonics create big problems for sensitive electronic equipment, and they must be mitigated through filtering or management.